Welcome, ladies and gentlemen, to our lecture on Kepler's laws. We've talked about uniform circular motion, and that's a good approximation for many orbits, but it doesn't work for all orbits, so it doesn't explain orbits in general. With Kepler's laws, we'll get a little more into describing the behavior of real orbits in the universe. So let's look at the shape of orbits. If orbits aren't always circular, what shape are they? And the answer is an ellipse. And an ellipse looks something like what I have here, where it's a curve around two focal points. These 2 points that I put here are focal points. And the definition of an ellipse, what's required for something to be an ellipse, is that every point along the curve, so for example this point here, the sum of the distance from the two foci is constant. Okay, so that is the same distance as, say, for this point where this, imagine I drew a straight line there, would also be the same distance. So this path length where I start, say, at focus 1 and end at focus 2 through a point on the circle. So this path length where I travel along from 1 to a point on the curve, and then from the point on the curve to 2, this path length is the same for all points on the curve. So if I travel from 1 to this point, and then from this point to focus 2, that path length is the same as this path length. So the path length AB is the same as the path length CD. Okay? That's the definition of an ellipse. So we can look at an ellipse and we can think about it having two most important diameters. Okay? The first is this diameter across this way, the longest diameter of the ellipse. This is called the major axis. Okay? And then the second one is this diameter here, and this is the shortest diameter across the ellipse. This is called the minor axis. And for each of these, when we talk about them, often what we talk about would be this length here. This is the semi-major axis, A. And this length here is the semi-minor axis that we'll call B. And you can see that these two semi-axes are kind of analogous to the radius of a circle, right? But the distance from the center here isn't always the same, right? It smoothly transitions from A to B. So it's not a circle. But a circle is actually a special case of an ellipse. So if I have an ellipse like this, as I move the foci closer and closer together, I get something that's more and more circular, okay? Now, my ability to draw this is limited. But I get something that's more and more circular, and at the point where I put the two foci on top of each other, I actually get a perfect circle. And the semi-major and the semi-minor axis become just one. They're just the same length, and it's the radius of the circle. Okay? And it turns out that objects orbit in the shape of an ellipse, with the center of mass between the two objects at one focus of the ellipse. So let's talk briefly about what center of mass is, okay, while we're on the topic here. The center of mass is the center of all the material of an object or a system of objects, okay? We find the center of mass by taking a weighted average of all the material. Then the average location of the mass is the center of that mass. So if we have an object here, and we think about the weighted average as taking some infinitesimal piece here, okay? Say this is a super tiny piece. Let's draw it even tinier than I've drawn it. We're going to take a super tiny little piece here. And for this piece, it has some mass. We'll say m1, okay? And let's say we have a coordinate system where the origin is right here. This distance, r1, from the origin, okay? And then you can think we could do that for all the little infinitesimal pieces, okay? All the little pieces that make up this object, all over it, until we've done all of the mass of the entire object, okay? Then we average up all of those little weighted averages, okay? It's the location weighted by the mass there, okay? We add up all of those little weighted locations, and then we divide by the total mass of the object. Okay, we just add up the mass of all those little pieces, and that's going to give us our center of mass. Now, that seems complicated, but it really isn't that complicated. When we have really nice geometric shapes that have a constant density, okay, like a billiard ball or a bowling ball before we drill the holes in it, the center of mass is just going to be in the geometric center of the object, okay? So for a billiard ball or for a bowling ball, before we drill the holes in it, it's just a sphere. If this little misshapen guy we could call a sphere for a second, it's just a sphere. And the center of that sphere is going to be the center of mass, okay? Because we have the same density, which means that in any one little volume we have the same amount of mass. And then we add up this thing in this perfect sphere. The center, the weighted average of all the mass, is going to be in the center of it, okay? The bowling ball, before we drill the holes, the center of mass is right here. But as we drill out the holes a little bit, right, you can see that if I drill holes in this, my center of mass is going to move just a little bit this way. Because if I took the area on this half, there's a little bit less mass on that half than there is on this half once I drill the holes in it, right? So I move the center of mass of the bowling ball just a little bit when I drill the holes in it. Now for a bowling ball, it's not much, right? A bowling ball is pretty heavy and we don't drill very big holes in it, okay? But we are going to move the center of mass a little bit by taking some of that mass away out of the bowling ball. So we have this formula up here for the center of mass, and it's really just a weighted average of the location of all the mass in an object or in a system of objects. But we can also see it really easily by thinking about balancing objects, okay? So for something like a ruler, if the ruler has a nice uniform density, then the ruler's center of mass will be in the middle of the ruler, okay? And you can balance a ruler on the end of a pen or your finger or something like that by putting it right under the center of mass, okay? In fact, it's a good way to find the center of mass of something by figuring out where it balances on your finger, okay? Now, the reason that it'll balance is because if I have my finger on the center of mass, that means that the amount of mass on this side of my finger is the same, okay, if that's M, is the same as the amount of mass on this side of my finger, okay? And that means that the force of gravity, mg, pulling down on this, is the same for either side. So as gravity pulls on this side, it would want to tip this way, right? It would want to have this side go down. But gravity pulls on this side with the same force, which would make it want to tip this way. And it doesn't end up tipping either way because we pull with the same force on either side, okay? They balance out. But now let's modify this a little bit. Let's take our ruler here, and let's say we put some weights on either end of the ruler. We put a weight over here, and we put a weight over here. And let's say that this weight is twice as heavy as this weight, okay? Now, at this point, the center of mass of our object here, it's not in the middle anymore, right? Because we have more weight on this side than we do on this side. So let's simplify this even further, and let's say that the ruler is massless. And then let's think about where the center of mass would be for these two weights, okay? So if I look at this system and I put my origin right here in the center of the big weight, then I can look at this thing and I can do my weighted average of the masses. So let's say the distance between the two weights is d, okay? In fact, let's be a little more precise here. Let's say the distance between the center of mass of each of the two weights is d. So now, when I go to write my center of mass for the system, remember it's just a weighted average. So I have R Cm equals, we'll call this one M1, and we'll call this one M2. It's going to be M1 R1, okay? The mass of the first object times its distance from the origin, and M2 R2, okay? And then we're going to sum up all the mass in the system, which is just the two masses right now because we said the ruler was massless, right? But then looking at our specific system, we see that we have M1 is 2m, right? And that's times its distance from the origin, which is 0, because we put it right at the origin, plus M2, which has a mass of m, and then a distance d from the origin. And that's divided by all the mass, right? So M1 was 2m plus M2, which was m. Now if we simplify a little bit, we see that we get md over 3m. And then if we simplify further, we see that we'll have 1/3 d. Okay? So when I look at this system, I find that my center of mass is 1/3 the distance d, which is, I don't know, around here somewhere. This is the location of my center of mass, okay? And this makes sense if we think about it, because if I have more mass over here, and I'm taking an average that's of the distances that's weighted by the mass, then this, because it has more mass, affects the average more than this mass, right? And so it moves the center of mass toward the bigger mass here. So that's the idea of center of mass, and that's how we calculate the center of mass. And you can get really nice demonstrations of the center of mass just by balancing different things on your finger. If you try to balance a ruler on your finger, you'll find that the center of mass is in the middle or near the middle of the ruler, okay, depending on the ruler and depending on what it's made out of and things like that. And you can balance the ruler on your finger by getting the center of mass right over your finger, okay? If you try to balance something like a hammer on your finger, you'll find that to balance it, you need to have your finger much closer to the head of the hammer because there's a lot more mass in the head than there is in the handle, okay? And that moves the center of mass toward the head of the hammer. So now let's return to the shape of the orbits, okay? We have these two foci for this ellipse somewhere like this, okay? And we know that these orbiting bodies interact through gravity, and both bodies orbit the center of mass of the system. So if we think about a planet and a star, we can always draw a line between the planet and the star. We can find the center of mass of the system, and it's always going to sit at the same focus in the ellipse, okay? So it doesn't move back and forth between the two foci or anything like that. Whatever focus it's on, it stays on that. And the center of mass always sits right on that focus, okay? And you notice when I draw the line through this looks just like our massless ruler example, right? So Now, all we have to consider is the mass of the planet and the mass of the star, okay? We find the center of mass, it sits at a focus, and the center of mass always sits at that focus, okay? Now, you can see as I move the planet and the star, if I want to keep the center of mass between the two of them always at this focus, you can see that I have to move both objects, right? I have to continually move both objects to keep this center of mass at the focus. And this is how orbiting bodies actually move, okay? Both objects move in an ellipse around one focus, okay? So each body has an orbit that's an ellipse, and for both of them, one focus of the ellipse of their orbit is at the center of mass of the system, okay? So with this knowledge, it must be true that the Earth doesn't orbit the sun with nothing happening on the sun's end, right? The truth must be that the Earth and the sun are both orbiting the center of mass of the system that the Earth and the sun comprise, right? So, where is that center of mass? What's actually happening here? If we consider, first off, that the Earth's orbit is very nearly circular, okay? So, the difference between its semi-major and semi-minor axes are very small, okay? And if we consider the Earth's average distance from the sun is 150 billion meters, okay? 150, let's use a D for this, okay? 150 billion meters, okay? And then we consider that the Earth has a mass of 5.97 times 10 to the 24 kilograms. And the sun has a mass of 1.99 times 10 to the 30 kilograms. Then we can estimate the location of the center of mass of the system, okay? It looks just like our massless ruler example, right? So let's put the origin of the coordinate system at the center of the sun. Then RCM equals the mass of the sun times its distance from the center, okay, from the origin, plus the mass of the Earth times its distance from the origin of our coordinate system. And that's divided by the sum of the mass of our two-body system. Okay? You can see that when we simplify, we'll just have the mass of the Earth times its distance from the center of the system here over the sum of the masses. And if we plug in these numbers, what we find is that the center of mass between the Earth and the sun is 450,000 meters away from the center of the sun. Okay? Because remember, that was where our origin was. So 450,000 meters sounds pretty far away from the center of the sun. But remember that the Earth is 150 billion meters away from the sun, okay? In fact, the radius of the sun is about 700 million meters. So, in astronomical terms, 450,000 meters is nothing, okay? It's much, much smaller than the radius of the sun. It's way smaller than the distance of the Earth from the sun. So, this is the reason that we're safe to approximate this system as the Earth just orbiting the sun. So we've learned now that technically, when we have orbiting bodies, what we actually have is each body orbiting the center of mass of the system of the two bodies, okay? And each of them orbits in an ellipse, and for each one focus of their ellipse is on the center of mass of the system, okay? So, for example, if I had some planet and a star, and the star was near this focus, the star has its own ellipse like this, okay? And the star will go around this ellipse, and this focus here will be at one focus of this ellipse. And then this focus is also at, obviously, one focus of the planet's ellipse. And they each go around their ellipse, and they keep the center of mass between the two objects always at this focus, okay? And this focus is one of the two foci of both of these two ellipses. But for a very large number of systems, we can approximate this as the larger body just sitting at one focus of the ellipse that describes the smaller body's orbit. Okay? This approximation is generally okay when the larger body is much, much larger than the smaller one. So, for the solar system, this means that we just say that the sun sits at one focus of each planet's orbital ellipse. Okay? For a planet, this usually means that the planet sits at one focus and all of its moons, okay, or space stations or satellites or whatever, orbit it in these ellipses that all have one focus just at the planet, okay? Now, there are planet and moon systems where the moon is big enough that this focus actually sits outside the planet, right? But usually we can approximate it as the focus just sitting at the center of the planet and things kind of orbiting around the planet. And this approximation, where the larger body sits at one focus of the ellipse, this is what Kepler actually took note of when he deduced these laws. In particular, Kepler was looking at the motion of the planets. So in Kepler's laws, we always have the sun sitting at one focus, okay? But Kepler's laws are actually laws about orbits. He noticed it as the motion of the planets, but they actually generalize to orbits. So for any system where we can make the approximation that the larger body just sits at one focus, Kepler's laws are going to hold for that system, okay? So when we have, say, the space station orbiting the Earth, or a satellite orbiting the Earth, or all of the different little moons that orbit Jupiter, in all of those cases, Kepler's laws are going to hold if we just replace the sun with the big body and the planet with the little body. So when we consider things in this approximation, where the very large body is at one focus of the ellipse, and the smaller body just orbits on the ellipse, we have a few definitions that allow us to talk about the orbit of the smaller body. Okay? Remember that we had the major axis and the semi-major axis. Or not the minor axis. And then when we talk about these orbits, we usually talk about their semi-major axis A. Okay? This is the quantity that we usually use to describe the orbit. And then we recognize that there's this semi-minor axis as well, okay, that we already learned about. And to describe an orbit, usually what we use is the semi-major axis, and we use a number called the eccentricity. And the eccentricity, E, is a number that describes how far from circular an ellipse is, okay, or an orbit is in this case. So E equals 0 is a circle, okay? Let's put it over here. E equals 0 is a circle. And then E greater than 0 but less than 1 is an ellipse, okay? And as we get closer to 1, if we think about an ellipse as kind of a squashed circle, closer to 1 is more squashed, and closer to 0 is more circular, okay? So we get increasingly squashed circles as we go closer and closer to 1, and our ellipse goes from being a circle to, as the foci get farther apart, more of a squashed circle, and then as they get really far apart, to something, very squashed. And then as our eccentricity goes greater than or equal to 1, we have an open orbit, okay? In this case, when the eccentricity is 1, we have a parabola that goes around the star, okay? And if it's greater than 1, we have what's called a hyperbola, and it looks like just a parabola that's even more open, okay? And these open orbits are things they would just be going through the system, and we call it an open orbit because you can see on this end, over in this area over here, these orbits don't come back together, okay? So this is just something going through the solar system. So if something were to kind of shoot through the solar system, some object that's in interstellar space, like the one that was seen recently by some telescopes here in Hawaii, that kind of thing would just go through in this parabolic or hyperbolic shape and pass through. It would be affected by the sun's gravity, but it's going so fast that it just passes through the solar system and it doesn't become trapped in an orbit around the sun. So then we have 2 points on the orbit that are important to us. We have periapsis right here, when the small body is closest to the center of mass of the system, okay? And in our approximation here, remember that periapsis is just when the small body is closest to the large body, because we're just putting the focus in the middle of the large body in this approximation, okay? But periapsis, even when we have the very real orbiting behavior where we have each object orbiting the center of mass of the system, periapsis is when you're closest to the center of mass of the system, okay? In Kepler's laws, we call this perihelion because Kepler was looking at planets orbiting the sun, and of course the root word helio always refers to something with the sun, okay? So Kepler called this perihelion. Then we have apoapsis, which occurs out here, where the small body is furthest from the center of mass of the system, okay? Or in our approximation, furthest from the big body, okay? And Kepler called this aphelion because, again, he's looking at things orbiting the sun, okay? So we have periapsis, when the small body is closest to the big body, and we have apoapsis, when the small body is furthest from the big body. So with those things defined, let's move on to Kepler's laws. So in the early part of the 17th century, this stuff was all in a book that Kepler published in, I want to say 1609, but it was somewhere around there, 1609, 1610, something like that, okay? The very early 17th century. Kepler published his laws of planetary motion, okay? And I want to be clear about the fact that Kepler's laws describe what planets do, okay? So Kepler said the sun sits here, and the planets go around it in this ellipse, okay? Now, Kepler couldn't explain why the planets do this, right? He couldn't explain why they act the way they do. And it wasn't until later, when Isaac Newton was proposing the force of gravity, that there was some explanation for why planets move the way that they do. Okay? Kepler was just saying that the planets do move this way. He was just making an observation about the universe. And the recognition that the reason things fall to the ground in your everyday life is the exact same reason that the planets orbit the sun, This was a monumental breakthrough, and that didn't occur until Isaac Newton. Newton, in fact, showed that Kepler's laws could be derived using his theory of gravity, all right? The one that we covered in the last lecture, that Newton's universal law of gravitation. He showed that we can derive Kepler's laws using that because ultimately the way that orbiting bodies behave is all down to gravitational interactions, okay? It all comes from gravitational interactions, and Kepler's laws aren't laws that explain why planets move this way. Planets don't just move this way because they're required to be in ellipses. They move this way because they have a force of gravity pulling on them, and that force has this 1 over r squared behavior, okay? That's why they move this way. So let's go to Kepler's first law. His first law is the thing that we've been discussing this whole time, okay? The planets move in ellipses with the sun at one focus of the ellipse, okay? That's Kepler's first law. So this first law is really simple to state, right? Just the planets move in ellipses. But it was a huge breakthrough at the time. So just to give you an idea of how big of a discovery this was by Kepler, as a student, Kepler actually wrote a scholarly paper in which he defended the idea that the sun is at the center of the solar system. Okay? So that's the stage of human knowledge that we were in at the time. Kepler had to write a scholarly paper defending the idea that the sun was at the center of the solar system, because that was still up for debate. And even for people that realized that the planets all orbited the sun, they still thought that everything must orbit in circles. Okay? They thought this because the circle was seen as a perfect shape, and they believed that the heavens should be ruled by ideal rules. Okay? So recognizing that the planets orbit the sun in ellipses was a pretty big deal at the time. So we've already learned that, in fact, both bodies orbit the center of mass between them, and that both bodies orbit in ellipses. But remember that in our solar system, the approximation that the sun just sits at one focus with the planets orbiting around it is a pretty good approximation, okay? The other thing about this is that the eccentricity of the orbits of most of the planets in the solar system is really, really small, okay? So it took really precise measurements, which Kepler got from Tycho Brahe, to realize that the planets were not orbiting in circles. So we said that closer to 0 is closer to a circle. E for the Earth, I think, is around 0.017. So what we're talking about here is a really small difference from a circle, okay? So you can see why other people, when they looked through telescopes and things at the planets, first off, it was incredible of them to realize when they looked up in the sky that some of the dots were not stars, right? They were different than stars. And then they realized that they were planets. And then they realized that they actually orbit the sun. It's not everything swirling around the Earth. Earth is just one more thing that's swirling around the sun. And then when they looked up there, the eccentricity of the orbits is really small. And they really wanted the heavens to be ruled by these perfect ideals. Okay? And so they said, well, the planets orbit in circles then. And then Kepler, with these really precise measurements from Brahe, went so far as to realize that if I really wanted to accurately describe the motion of the planets, they actually move in ellipses, okay? And the sun is at one focus of the ellipse. And this really was a huge breakthrough to show that the heavens are not a place ruled by ideals after all, okay? And if we want to describe things, we can't rely on our desire for them to be ruled by perfect rules. We have to mold the rules to describe the behavior that we see in the universe. So now let's look at Kepler's second law. And Kepler's second law is that the planet will sweep out an equal area of the ellipse in an equal amount of time. Okay? So if I have my focus here, and I have the sun sitting at this focus, let's say that my planet in a given time, let's say 15 days, it sweeps out a little area like this, okay? So let's say in 15 days the planet moves this far, and that sweeps out this area of the ellipse, okay? And that area has some finite magnitude, right? It's some finite amount of area. It isn't very thick, but it's really long, right? It isn't very big this way, but it's really long. And so the area adds up to some decent amount of area, okay? Now, when I look at this and my planet is close to the sun, Kepler's second law tells me that in 15 days I have to sweep out the same area of the ellipse over here as I did over here, okay? So in an equal amount of time, in this 15 days, I have to sweep out an area, but now you can see my area is going to be a lot shorter, right? So to make up for it, I'm going to have to make it wider, okay? So to sweep out the same area on this side, it might look something like this, okay? Now, is this drawing perfect? Probably not. But something like this. So it sweeps out that area in 15 days. Now, to make this area here equal this area here, I had to make it a lot wider to make up for the fact that it's shorter. And the consequences of Kepler's second law is that the small body moves a lot faster as it gets closer to the large body, okay? So if I cover this in 15 days, you can see I'm not moving very fast, right? I just go from here to here in 15 days. But then to sweep out the same area in 15 days, I have to cover this whole arc. And this arc is a lot bigger than this one, right? So if I go from here around to here in 15 days, that's a lot further than here to here. So I have to go faster, okay? And this realization shows that the planets move at differing velocities as they go around the ellipse, okay? Their velocity is still going to be tangential to the ellipse at any point, okay? But the velocity is changing as it goes around all the time. The velocity is changing, and it moves fastest right here at periapsis, okay? Fastest at periapsis, okay? And it moves slowest over here at apoapsis. And Kepler's second law here describes this behavior of this constantly changing velocity of the planets and what that velocity must be, okay? We can always calculate it by calculating the area of some arc when it covers some set time, and then we can calculate what the velocity must be for any other amount of time in any other part of the orbit. So now we come to Kepler's third law, and let's actually start with what Newton showed. So Newton derived this equation for the period of a small body around a much larger body, okay? And in this equation, A here is the semi-major axis. So if we have our two axes like this, A is this semi-major axis of the ellipse, okay? G is Newton's gravitational constant, which we had from the last lecture. M is the mass of the big body. So if this is one of the planets and we have the sun here at one focus, this would be the mass of the sun. And T is the period, okay? The time that it takes to complete one full orbit. So what's notable here is the fact that this period does not depend on the eccentricity of the orbit. Okay? So as long as I have this same length of semi-major axis, I'll have the same period for the orbit. So if I have this situation where the foci are not very far apart, so I have something that's much closer to circular, if this orbit is big enough that this A is the same for my more circular orbit and for this much less circular orbit, their period lengths will actually be the same if they're both going around the same mass here, right? If this big M is the same. So if I'm orbiting the sun, then the length of the semi-major axis of my orbit completely defines what the period of my orbit will be. And Kepler realized that for all the planets, if we write the equation t squared equals b a cubed, where t is the period and a here is the semi-major axis, then this constant b, Kepler realized that it was the same for all the planets in the solar system. Okay? And this was later generalized by Newton to be this equation for the period when we have some small body orbiting some much larger body. So Kepler's third law comes about as a consequence of the relationship between a planet's gravitational potential energy and its kinetic energy. But those are concepts that we haven't discussed yet. In our next lecture, we'll begin to move past Newton's laws of motion and we'll start to talk about energy.